This non-equilibrium condition awakens molecules to a coherence that's not evident when the molecules are in equilibrium.
At equilibrium, molecules behave as essentially independent entities. They ignore each other. We would like to call them hypnons, sleepwalkers. So each of them may be as complex as we like. They ignore one another. However, non-equilibrium wakes them up and introduces a coherence quite foreign to equilibrium. The microscopic theory of irreversible processes will present a similar picture of matter.
The study of far from equilibrium systems is a far cry from the historical assumptions of physics. Equilibrium has for more than a century been assumed to be nature's goal. Ever since Boltzmann's second law established the idea of entropy, physicists have believed that nature inevitably progresses toward an equilibrium of inert uniformity, that is, toward a total lack of order and complexity. Now the theory of self-organizing systems has shown that equilibrium is not nature's goal. Just as Newton's theory of motion overturned Aristotle's idea that objects are naturally at rest, self-organization theory has overthrown the idea that nature itself necessarily seeks to be at thermodynamic equilibrium. Indeed, far from equilibrium systems seem to be responsible for many of nature's most vital and interesting features, including life itself. Generally, when a system is pushed further away from thermodynamic equilibrium, it can enter an increasing number of distinctly different states. Moving away from equilibrium is very similar to the transition to chaos. Earlier, we saw that when we increase a system's intrinsic rate of growth, its attractor goes through a cascade of bifurcations, leading to ever more complex cycles. If a system is not in equilibrium, increasing energy inputs result in more bifurcations. This leads to an ever greater number of possible states within the system, where each state represents a different structure. In the Earth's atmosphere, which is quite far from equilibrium, many coherent macroscopic phenomena can be observed. These exist at all scales, from the little whirlwind blowing leaves on the sidewalk, to a thunderstorm drenching a city, to a low-pressure system covering part of a continent. Each is locally stable and maintains itself for a time. We might say that the far-from equilibrium atmosphere has many attractors, a thunderstorm attractor, a tornado attractor, and so forth, each with its own basin of attraction. This bifurcation process is essential to self-organizing systems. It is how a disequilibrium system tends to become more highly organized, more complex. As we'll see, to understand self-organization is to understand important new concepts of both time and history. In a sense, we'll even be able to say that history is hidden in the mathematics of bifurcation.